dx dt equals ax plus by, and dy dt is cx plus dy. That's called what kind of a system? Linear. It's a linear system because it's linear in both x and y, right? All the exponents on the x's and y's are ones. Linear. Oh, sorry. AD minus BC, that's a special value, and we call it the determinant. All right, and the matrix ABCD is called the blank blank of the system. Coefficient matrix. Matrix made up of the coefficients of the linear system. Okay, so we're going to start with a little mini linear algebra lesson. So people who've had linear algebra, this will be a quick review. And if you haven't, this should be all that you'll need moving forward. Okay, so we're going to use the concepts from linear algebra when studying linear systems. So that kind of makes sense. They're both linear things, so it's a tool that's going to be helpful to us. So a vector is just a list of numbers. We typically are going to write them vertically. Sometimes your book writes them horizontally when they are writing answers and stuff, just to save paper. But I typically write them vertically. And most of you, all of you have had Calc 3, so you've seen vectors, right? A matrix is just an array of numbers, a grid of numbers that's made up of column vectors. So if each column of the matrix could be thought of as a vector, and you just put them all together and they make a matrix. Okay, the size of a matrix is described by giving the number of rows and then the number of columns, and you always give it in that order, rows, columns. So this matrix has 1, 2, 3 rows going across, 3 across, and 2 columns going down. So we call that a 3 by 2 matrix. 3 rows, 2 columns. All right, so here's the part that if you haven't had linear algebra, this is a little crash course in matrix arithmetic. Okay, so to multiply 2 matrices, the number of columns in the first matrix has to equal the number of rows in the second matrix. And the product of the 2 matrices is going to have the number of rows from the first and the number of columns from the second. So I know that sounds wordy, but we'll do an example and you'll see. So if you're going to multiply a 3 by 2 matrix, 3 rows, 2 columns, by a 2 by 4 matrix, 2 rows, 4 columns, the inner dimensions, right, these guys have to match in order to be able to multiply them. And the result will be these outer dimensions, 3 by 4. Okay. And to multiply 2 matrices, I know in Calc 3 you talked about the dot product. So I'm going to use that. To multiply 2 matrices, you take the dot product of each row in the first matrix. So I would look at this row, right, with each column of the second matrix, right? So for each row and column, you take the dot product, and you fill in a matrix. So this matrix, or this product, my first matrix is 3 by 2, and my second matrix is 2 by 2, right? So can I multiply those two together? Yes, because the inner dimensions, the 2's match. What's the result going to be? 3 by 2. Okay, so this is how I like to do it. I like to sort of draw in my matrix, and it's going to be 3 rows, 2 columns. So I'm going to just sort of put in blanks. 3 rows, 2 columns. Then I'm going to fill in as I take the product. Okay, so like I said, each of these entries is going to be found by taking the dot product of a row and a column. A row from the first matrix, a column from the second matrix. So to fill in the answer matrix, to fill in the first row, first column of the answer matrix, space 1, 1, first row, first column, you multiply the first row and first column of the two factors. Okay, so I'm going to multiply first row times first column, dot product. Anybody remember what the dot product is? Yeah, it's going to be a scalar. It's going to be a single number. So this is what I picture. I picture taking the 1, negative 2, like I could pick up that whole row, turn it 90 degrees, lay it on top of the 1, 3, and the numbers that match up, you multiply together, and you add the results. So 1 is going to be on top of 1, so 1 times 1 is 1. Negative 2 on top of 3, negative 2 times 3 is negative 6. 1 plus negative 6 is negative 5. So I'll write it out here. 1 times 1 plus negative 2 times 3. That's the dot product of the first row, first column. Now, if I want to fill in first row, second column of my product, I multiply the first row, second column of my factors. So my dot product would be 1 times 2 plus negative 2 times 4. To do second row, first column of the answer, take the second row and the first column from the two factors. Dot product 1 times 1 plus 5 times 3. Is this, do you kind of get the pattern? Okay. So if I finish up my second row, second column would be 1 times 2 plus 5 times 4. And then I have 1 times 1 plus 7 times 3. And 1 times 2 plus 7 times 4. Okay, so my final matrix is going to be negative 5, 16, 22. Negative 8 plus 2 is negative 6. 22, 30. If I did all that arithmetic right. Negative 6, negative 2 times 4 is negative 8, plus 2 is negative 6. You can use a graphing calculator to multiply matrices, but for the purposes of using them in differential equations, we're mostly going to be multiplying really small stuff, like a 2 by 2 by a 2 by 1, like really small things. So it's easier to just know how to do it in your head. And sometimes you're going to have letters and not numbers. Okay, so matrices are usually named with a capital letter. Vectors are usually named with a bold letter, or a letter with an arrow on top of it. Your book, I believe, is strangely also using a bold letter for naming matrices. I don't know why. Some books do, some books don't. So you'll have to know which is a matrix, which is a vector. All right, that's it for linear algebra. That's everything you should need to know for now. All right, a linear system is a system that looks like x prime is ax plus by and y prime is cx plus dy. And we can write a linear system much more efficiently using vector and matrix notation. All right, so we're going to let A be the 2 by 2 coefficient matrix, right? So that's just grab the coefficients, whatever they are, from your linear system, A, B, C, and D, and throw them in a matrix. And we're going to let Y, bolded because it's a vector, right, be the column vector of dependent variables x and y. So let's look at what happens when we take the product A, the matrix A times the vector Y. Okay, so I've got A, B, C, D. Oh, also something, people who took linear algebra, you're used to seeing matrices in square brackets. You can put them in curved brackets. It's all the same thing, just a slightly different notation. Okay, so I'm going to do A, B, C, D, that's A, times Y, which is X, Y. This is A. This is y, the vector y. Okay, so now we're going to use what we just learned, how to multiply matrices. Okay. What is the resulting matrix going to be? What's its size? 2 by 1. Yeah, we've got 2 by 2 times a 2 by 1. The inner dimensions match. They're both 2's. The result is going to be a 2 by 1. So 2 rows, 1 column. You can sort of put in spaces for where the answers go. We take the dot product of AB and XY, and you get AX plus BY. And then take the dot product of CD with XY, and you get CX plus DY. Right? That is the right-hand side of our linear system, right? And if we're letting Y be the column vector XY, bold Y is the column vector XY, then bold Y prime is the column vector X prime Y prime, and we can write the linear system as Y prime, the vector Y prime, is A times Y, so the matrix ABCD times the vector XY. This is X prime, Y prime. So it's a lot of new notation. It will come in handy, so just kind of push through it. It is, I wouldn't make you rewrite things in a different way if it wasn't useful. Any questions on that? Okay, so the harmonic oscillator that we've been talking about, damped or undamped, can be written as a system. Y prime equals V and V prime equals blah, right? And that is a linear system, right? Because you only have ones on the Y's and the V's. So the methods we're going to learn for linear systems can be used to analyze the harmonic oscillator. But we have a much more interesting example. We could also model all kinds of things besides the mass on a spring, for example, love affairs. So let's say Romeo is in love with Juliet. But in our version of the story, Juliet is fickle. And the more Romeo loves her, the more she wants to run away and hide. He's very smothering, right? So, but then when Romeo gets discouraged and backs off, he's like, fine, you're not interested. Juliet begins to find him strangely attractive again. But Romeo, on the other hand, tends to echo her. He warms up when she loves him and grows cold when she hates him.
Go for somebody else. Like
we could probably write a system that yeah, yes. Yeah. Here is the line and it's over. All right, so positive values of R and J signify love. So R is going to be Romeo's love or hate for Juliet at time t. J of t is going to be Juliet's love or hate for Romeo at time t. When we have positive values of R and J, those are going to signify love, and negative values are going to signify hate. So I want to write a system of differential equations that might model this situation, right? So how I want to express how Romeo's love for Juliet changes and how Juliet's love for Romeo changes based on how they and the other person feel. Okay, so let's talk about Romeo. So Romeo's love changes, right? And it changes, let's see, Romeo echoes Juliet, right? So when she loves him, he loves her more, right? So, and when she grows cold, and he grows cold when she hates him. So his love changes based on Juliet's feelings entirely, right? So I'm just going to put R dot is some constant times Juliet's love. It's proportional to Juliet's love. So when A is positive, right, meaning Juliet loves Romeo, his love is increasing. If A is negative, that Juliet doesn't like Romeo and his love is decreasing. And then let's look at Juliet, how Juliet's love is changing. Okay, so Juliet, when Romeo loves her, she doesn't want anything to do with him, right? So, yeah, negative some gamma r, right? It's sort of negatively, it's proportional, but it changes in the opposite direction, right? When Romeo loves Juliet, Juliet's love is decreasing, so we make it negative, right? And when Romeo hates Juliet, we take the opposite, and Juliet's love is growing. All right, so I'm just going to take, for the purposes of trying to analyze, like what's going to happen with these two? If they get together, can their love last? Right? Will they make a good couple? So to analyze it, I'm just going to choose the easiest values for the coefficients. And we're going to say r dot equals j and j dot equals negative r. Just choose one for both coefficients. And this is going to be the system that models their feelings. So we chose one for the constants. Here's the direction field for that system. Okay. With a phase portrait, I've got lots of solution curves sketched in there. What does this picture tell us about Romeo and Juliet's fate as a couple? It's kind of a roller coaster. Yeah. You suggested that it might be a sine wave, right? Yeah. It is cyclical. Yeah. So in the first quadrant, that's the only time they both love each other, right? So 25% of the time, they are in love with each other. Yeah, yeah. So they do both love each other, but their love is decreasing, right? 25% of the time, they're in love with each other, but both of them have their love decreasing. Yeah. And then in the third quadrant, they hate each other. Right? They hate each other. And then in the other two quadrants, one is in love with the other, but the other one hates them. Right? So this is kind of a sad on again, off again roller coaster. That will just continue cycling through these phases over and over and over again forever. Any questions? All right, so in your activities, you start out with some boring, like rewriting things with matrices, and then the last question is a different system about Romeo and Juliet.